Hello, welcome. My name is Isaac Agbozo. This is my YouTube channel. Today we are going to talk about the arithmetic logic unit, and we are going to analyze a circuit, and we are going to talk more about it. Why do we need the arithmetic logic unit? What is it? What does it do? The importance, sorry. Let's get into it. So we're given this circuit diagram below here. It shows an arithmetic logic unit design, okay, capable of performing four fundamental arithmetic operations. This presentation analyzes the circuit's architecture, functionality, and operational principles. So the arithmetic logic unit, or the ALU circuit, is designed to perform four distinct arithmetic operations on two input operations or operands, A and B, with an optional carry in or the C in. The operation selection is controlled by a 2-bit binary code, making it a versatile computational unit suitable for processor and architectures. Okay, so the ALU is part of the CPU. So the CPU is divided into two. It's divided into the control unit and the arithmetic logic unit. So we are talking about this part of the CPU that deals with computations. Okay, so the functional units of the ALU are the ALU supports four primary operations. Okay, that is addition operation, subtraction operation, multiplication operation, and division operations. Now, the ALU is divided into two sections, okay, the upper section and the lower section. The upper section is the arithmetic processing unit, okay. The upper portion contains the core computational elements. The subtraction module is dedicated for subtraction operations, okay. The multiplication module is specialized circuitry for multiplication. Division module is division computation unit, and the multiplexer, it selects appropriate output based on the control signals that is received by the computer. Okay, and now let's talk about the lower section, the control logic system. The control logic generates selection signals through the AND gate logic. So the AND gate logic, processes input combinations, that is A times B or A and B. It also has the complex logic operations. The complex logic operations handles A times B and C in combinations or carry in combinations. And we also have the signal distribution. The signal distribution routes control signals to the multiplexer. Now, let's talk about the operation principle. The control signal generations. The 2-bit control input determines which arithmetic operation is executed. Okay, 1. Control bits are processed through the lower logic section. 2. Logic gates generate appropriate selection signals. 3. These signals control the multiplexer in the upper section. Okay, and 4. The multiplexer routes the correct operational result to the output. Is that clear? Now, let's talk about data flow. So input operands A and B enter both the arithmetic unit and logic control. Now, the carry in provides additional input for operations requiring it or operations that need it. So all arithmetic operations are computed simultaneously, and the multiplexer selects the appropriate result based on the control code. Now the selected result appears on the output. So when the user, okay, or me, when I input operations or the operands A and B, they are both inputted into the arithmetic units, okay, and all operations. If when I say operands A and B, I mean values. okay, or raw numbers like maybe 3 and 4. Okay, let's say 3 and 4. And I use the arithmetic operation addition. I say 3 plus 4, or multiplication, 3 times 4. Now the duty of the ALU is to compute it. Okay, so now when that is done, the multiplexer will select the appropriate result based on the control code. If I used 3 plus 2 or 3 plus 4, okay, the multiplexer's job, okay, is to select or is to choose which one is correct or which one is the correct answer, whether it is 7 or it is 8, to pick the 7 for me, and it will display it as output to come out as the answer output. So that is what goes on behind the scenes when you type 3 plus 2 or 3 plus 4. Now, what are the advantages of this circuit, this arithmetic logic unit circuit? It helps in parallel processing. This approach maximizes throughput for applications requiring different operations. It also helps in modularity. So each arithmetic function is implemented as a separate module, which enables independent optimization of each operation. And there is easier testing and verification. There is also simplified maintenance and upgrades. Okay, another advantage of this circuit is flexibility. The 2-bit control scheme allows for easy expansion to addition operations if needed, making the design scalable for enhanced functionality. Okay, now what can we use this circuitry for? What are the uses of this circuitry? So processor integration. This ALU design is ideal for microprocessor arithmetic units, digital signal processing applications, embedded system controllers, calculator implementations. So yes, like the example I gave earlier. So when it's the chip or the circuitry is used in calculators, you see the logic behind it, that it helps in the computations, helps you get your numbers faster and more accurate. Now, for educational purposes, the ALU can be used, or it serves as an serves as an excellent teaching tool for digital logic design principles, computer architecture concepts, multiplexer applications, and arithmetic circuit implementations. Right. So this ALU or arithmetic logic unit circuit represents a well-designed arithmetic processing unit that efficiently combines multiple mathematical operations into a single controllable system. The use of parallel computation with multiplexed output selections provide both performance and flexibility, making it suitable for various digital computing applications. My name is Isaac Agbozo. Thank you.